So loading the registers, storing the content of the register to the memory location. Okay. So load store architecture means loading the register and storing the register, as you see in the screen. In the top left corner, you have an ARM processor core where you have a ALU. And there are register banks like R0 to R15, 16 registers available here. And there is a memory area is separately available. Okay. So processor cannot directly interact with the memory. Processor can only interact with the register. Hence, load store architecture comes into picture. Load means registers are loaded from the memory location. Store means register contents are stored to the memory locations. Operation cannot be performed with memory in ARM. Which operation cannot be performed with memory? Normally, if you look at the screen, MOV A, 30H. This we will do normally in 8051, where the content of the 30th memory location will be copied to the accumulator. So directly we can load the accumulator with the 30th memory location, which is not possible in ARM. Similarly, content of the accumulator is moved directly to the memory location through MOV 30H, A. That is also not possible in ARM. So the accumulator or the processor cannot directly interact with the memory. Processor cannot directly interact with memory. That alone is sufficient. We will experiment it now soon. We will understand this. Okay, so this is the instruction that we are about to see now. Okay, so we are loading the direction register with FFFF. Okay, so IO0 direction register occupies the memory space of E0002 to 8008. I am pointing the memory location of the peripherals. E00 to 8008 is the IO0 DER memory location. While executing this instruction, move negate, move the register R0 with the immediate constant 0000 and then complement the R0 content. Complementing the R0 content means it will become FFFF after executing this instruction. Let me do the single step. Now you see MOV MVN R0, hash is executed and R0 is loaded with 0 and then it is complemented. So R0 content is FFFF. And loading the register R1 with the GPIO memory locations of IO0 DER. What is the GPIO memory location of IO0 DER? Just now we have seen E002 and 8008. You will see R1 will be loaded with E002 8000. Okay, so GPIO's memory map is loaded to R1. Now what is happening? Now R1 is loaded with this address. R0 is having this value. Now storing the content of R0, to the memory location pointed by R1 plus add this 8 to it. So R1 is pointing E002 8000. If we are adding 8 to it, then E002 8008 to that particular location, content of R0 will be stored. Let me do the single step execution. We are able to, it is executed. Now the content of R0 is moved to E002 8008 where FFFFFFF. Okay. Now we are about to execute the second instruction A equal to 0002. In the disassembly window of KEIL IDE, we are able to see 3 assembly language instruction was written for this C instruction. Let us see what this is doing. We will try to understand up to some extent. So as usual, MOV R0, hash 2. So R0 is loaded with the immediate constant 2. Very clear. Here also the same 8051 like kind of instruction. MOV R0, hash 2. But only difference is here it is 32 bit, that is 8 bit. Let us check. We do the single step execution and let us check. R0 will be loaded with 2 R0. Yes, we loaded with the single step instruction. R0 is loaded with 2. The whole instruction was executed. R0 is loaded with 2. And R1 is loaded with 4000. Why 4000? 4000 is the data memory location. Here you see, this is the peripheral location. I have shown the another memory location, right? 4000 is the memory location where the 2 is loaded with respect to LPC2148 microcontroller. The memory starts from 4000. On chip static RAM, variable occupies the memory space of 4000. That is what we have shown. So in the KEIL IDE, if you see, we are having only 4000, memory window of 4000. Memory window of 4000, we are having the variables. Okay, so variable A is having the value 2. So the content of the variable A is having 2. It is occupying a 32-bit space in the data memory, which is called as random access memory or static RAM, which is 4000. Now our next instruction, B is to be loaded with 4. How to load B is loaded with 4? Again, move R0, 4. Move R0, 4. R0 is loaded with 4. And R1 will be loaded with the data memory address. Yes, R1 should be loaded with the data memory address 4004. Because 4000, 4001, 4002, 4003, those 4 bytes are for variable A. Now 4004 is for variable B, where the 4 need to be stored to the data memory location pointed by R1. So R1 is pointing 4004. Within bracket, if you give means it is nothing but the memory location. There, if you put at symbol, that is memory location in 8051. Here within bracket, if you give means it is memory location. So it is indirect addressing. So don't go to the R1. So R1 is pointing some memory location. R1 is having some value, that is the memory location, which is 4004. And store the str means what? Store the content of the register R0 to the memory location pointed by R1. R1 is pointing 4004. So content of R0 is 4, which is to be loaded in 4004. So this is load store architecture. Yes. Now 4004 is loaded with 4, 2 and 4. And we are loading D with 22. Okay. Variable D with your load. Loading the variable D with 22. D is a character variable. Now you see, move the register R0 with 22 as usual. Move the register R0 with 22. R0 is loaded with 22. Loading the register R1 with value. Loading the register R1 with the value of 4000C. So in the 4000C, we are storing the content of R1. It's storing the byte. B means str B means storing the byte value, the byte variable. Why byte variable? The variable D is a character variable. So storing the byte variable to the register R1. Okay, R1 is pointing some memory location which is 4003, 4000C. Okay, store the content of the register R0 to the memory location pointed by R1. R1 is pointing 4000C. So store the content of register R0. R0 is 22. So 22 has to be stored into the memory location pointed by R1. R1 is pointing 4000C. What is there in 4000C? 4000C is already there is 22. This already has been executed. So once again I am just overwriting it. So 24. And similarly other bytes. E is loaded with 44. So register R0 with 44, R1 with D, next byte, and store the byte. So 44 is stored to the next one. So 22, 44. So this is C, this is D. Now what are you doing? What we are doing? We are branching to 320, yes, and again we are branching to B means branch instruction. 27C, we are branching to 27C. Here it's very interesting. You are adding the content of A and B. You are adding the content of A and B. Content of A is what? Content of A is what? 2 and 4. So adding the content of A and B. For that, just like that, it cannot add. We keep on doing the load instruction, and after adding, it brings the return address, store address. Then finally it is storing the R0 content. We have written one single C instruction called C equal to A plus B, but it has written 1, 2, 3, 4 load instruction and 1 add instruction. This load is to bring the address of the destination. Then content of the register R0 is stored to that. Let us see how this. Actually 4 plus 2 equal to 6. Let us see how this is happening. So loading the register R0 with the memory location pointed by program counter. So 4 has brought 4000. R0 is loaded with 4000. 4000 content has to bring to the R0. In 4000, what is there? In 4000 we have 2. In 4000 000. In the memory location the value is 2. So bring the content of R0 to R0. So R0 is pointing some memory location which is 4000. Go to that location, bring the value. In this location we have 2. So 2 has to come to this R0 after executing this instruction, which is pointed by the program counter, which is R15, which is 280. So it is pointing 280 from here. You see single step. So R0 is loaded with 2. Now again R1 is loaded with the second value. So R1 should be pointing 4004. In 4004 we have a second value which is 4. You can see 4000 at 4. Second value 4. So the R1 has to load the R1 pointed value. R1 is pointing 4004. In 4004 we have the value 4. So that 4 will be copied to R1 after executing this instruction. So R0 is having 2, R1 is having 4. These two has to be added, and R0 is something like accumulator. The result will be stored in accumulator in ARM core. That is what you see. Add R0, R1, R0, R1. These are all possible in ARM instruction. This is one thing you need to understand. So we are learning ARM architecture and instruction set in ARM processor and 32-bit. Things are happening just like that, as we see here. So add the content of R0 with R1 and store the result in R0. That is what this shows. Add R0, R0, R1. You see 4 plus 2 equals 6 after addition. Then we are identifying the memory location. We are identifying the memory location of the variable C. So C is the variable which is available in the memory location 4008. So store the content of the register R0, which is the sum of the two numbers, to 4008. That is str R1. R1 is pointing 4008. Store the content of register R0 to memory location pointed by R1. R1 is pointing 4008. Yes, 4008. 4 plus 2 equals 6. 6 will be there in 4008. That is executed. 6 will be there in 4008. Similarly, F equal to D plus E means what? It's very simple. You are adding the byte, right? You are adding the byte instruction. Did you see? F equal to D plus E means similar, same thing is repeated. Load register and load byte, load register, then load byte, adding this and same thing, right? You see? Load the register R0 with the value which is 4000C. So copy the content of the register R0. In 4003 we have 22. So 22 has to come to R0. Then loading the register R1 with the address, byte address. That is why LDR. Then LDRB means load only the byte. Load only the byte. Hence 22 and 44. Then the add R0, R0, R1 means adding these two. So 66. 66 is the sum which has to be moved to the 4000E. So here you get 4000E, CDE. 66 has to be moved there. CDE. So E is having 66. Okay. And finally it has to move to the 66 has to come to IO0 pin. That is IO0 pin. This is IO0 pin. 66 has to come here. So for that we have to find out the address of IO0 pin. Okay. IO0 pin is what? That is IO0 pin. It is 8000. E002 8000 is the address of IO0 pin. You see. Look at the screen. Look at the cursor. The data sheet of LPC2148 microcontroller. The pin is IO0 pin. Is occupying the data memory location E002 8000. So we are expecting E002 8000 location must be loaded with 66. E002 8000. Here we are expecting 66. Okay. So I am having two memory locations, two memory windows. One memory window for pointing the SRAM, where the variables A, B, C, D, E, F, where the SRAM. This is SRAM memory location, and memory 2. This is, and memory 1 is peripheral memory GPIO. So to E002 8008 is IO0 DIR. E002 8000 is IO0 pin. We are expecting 66 here as per this. Let us see what is happening. So where is the program counter? Program counter is pointing this location. Now you see load R0. Our interest is to move the content of the variable C to the pin. So C is nothing but some memory location. So bring the value of C to the register R0. Address 4080 is the C variable address. You can see 4080 is the C variable location address, which is 6. So 6 has to brought to R0, right? So load R0, load the register R0 with 4008 and load the register R0, load the register R0 with the content of the memory location pointed by R0. R0 is pointing 4008. So bring the content of 4008 to the register R0. 4008 is containing, 4008 is having the value 6. 6 has to come to R0. This after executing the single step, 6 has come to R0. Then LDR R1 comma. So we are bringing in the destination address to R1, which is E002 8000, which is pin address. So move the content, store the content of the register R0 to the memory location pointed by R1. R1 is pointing E002 8000. E002 8000 is what? IO0 pin, which is visible in the window like this, IO0 pin. So here we are able to get 66 after executing this instruction. See? Here we are able to get 66, you see, which is bringing out to the pin. So 2 LED will switch on, 66. So IO0 pin is having 11, and here 200. E002 8000 is also having 6. This is how your ARM assembly language instruction is also working. And again IO0 pin equal to F. Again you are moving the variable F. Our content of F is 6. Content of F is 6, which is 16-bit, 8-bit value. So 66 has to be moved to the register. 66. And you are incrementing the variable A. Just we have written a C program called A equal to A plus 1. So for incrementing this variable, it has written some instruction like this. So you always load, store, and then only operation. That is the moral, right? Loading the register R0 with the address of the variable A and bringing the content of the variable A, incrementing the variable A and having in R0, and loading the destination addresses 4000 and sending back the incremented value to the register R0, R1. R1 is pointing 4000, so R0 is incremented to 3. So in 4000, the value should be 3. You can see in the location 4000 value should be 3. Similarly, 4 has to be incremented. That is what the C code which we have written, right? A equal to A plus 1, B equal to B plus 1, C equal to C plus 1, D equal to A plus 1. We are supposed to increment. So A equal to A plus 1 is over. Now we have to do B equal to B plus 1. How to do that? Bringing the load store instruction. Again, load store instruction. Load 4004. Bring the 4004 content, which is 4. Increment it. That is add R0, R0, hash 1. So it has become 5. Bring the destination address, which is 4004. Send back this current of R0 to the register pointed by R1, which is 4004. And 4004 is what? 4, which will become 5 after executing this instruction. Why? Because after incrementing, R0 content is moved to this. So 5. So 3 plus 5. It should be 8. Then C has to be incremented. Current of C register has to be incremented. So bringing the location, bringing the content, adding this to 7, sending back to bringing the location address, loading the location address, then storing back the 7 into the corresponding location 7. So 3, 5, 7, something like that. And again, here it is incrementing the D variable. Here it is the byte variable. So bringing the loading the R0 with the destination address and bringing the variable address, bringing the content of the variable address R0 to the variable R0. So 22 has come, and then you are incrementing to 23. Then bring the address 4000C and loading the 23 into 4000C. 23. So this will become 45. This will become 67. Similarly, So branch to 7C. Here C equal to A plus B. As usual, you are loading, incrementing. It goes on like this. So ARM assembly language instructions are happening more comfortably. So nothing difficult. Instead of 8-bit, everything is happening 32-bit that you need to understand. That is what the moral. So this is load store architecture where 8008 is loaded with FFFF. That's what. The same thing, right? The variable A is loaded with 2. That is what being shown. And here R0 register is loaded with 2, and the store the R0 connected to the data location of the variable A. And that 2 is loaded there to the 4000 more location, which you have seen already now. Okay. And again B is loaded with 4, and it is stored. B is loaded with 4, which is being shown in 4004. That is what we have seen right now. And D is loaded with 22. This B is loaded with 22, which is a byte variable. Hence, it occupies only 1 byte. strb byte variable. That is byte 22. And similarly, E is loaded with 44. Yeah, E is loaded with 44, which is a byte variable. That's why CB. This is the architecture of ARM Cortex M3 processor architecture. So look at inside. If you look at the Cortex M3 or M4 architecture, one thing you have to see: fetch, decode, execute. There is an instruction register. Instructions need to be fetched. Instruction need to be decoded. Instruction need to be executed. What happens in 8051? While fetching, decoding will not happen. Executing will not happen. While decoding, fetching will not happen. Execution will not happen. While executing, fetching will not happen. Decoding will not happen. Here, the name 3-stage pipelining means when the first instruction is getting decoded. In the first instruction is fetched first. Then, after fetching, while the first instruction is getting decoded, second instruction will be fetched. That's very interesting. When the first instruction is getting executed, by the time first instruction is getting executed, second instruction will get decoded, and the third instruction will get fetched. So this is 3-stage pipelining. So because of pipelining, 3 times you can increase the speed of the execution. Yes, because while executing the first instruction, second instruction will get decoded. By the time third instruction will get fetched. So it is pipeline. Hope you understand, right? This is the register bank. So in 8051, this register bank is in data memory, but in LPC2148, in Cortex M3, in Cortex M4, in general, in ARM processor core, those registers are sitting inside the processor core. This is the one difference. So the registers are not in the memory mapped location in the data memory. This R0 or R15 are present inside the processor architecture, as you see here, which is register bank. Okay. So there is something like memory interface, which is your program memory, program counter kind of things. And this is what the fetch, decode, execute, register bank, and memory interface kind of things. And there is something like floating point unit. We will be discussing about this in detail, which is something like 0.1 plus 0.1 equal to 0.2. This color, light color, this kind of light brown color, they are all for debugging. Instruction trace interface, breakpoint unit, watch point unit, data trace, software trace, embedded trace, macro cell, trace interface, debug interface, and all to debug, to simulate, to emulate, and so many things. These are all debugging supporting things. And there is something like interrupt. NVIC means nested vector interrupt controller. So all the peripherals will interrupt the processor through NVIC, nested vector interrupt controller, in the architecture as you see here. So interrupt controller is a part of the processor, not a separate peripheral. That you need to understand. So the register bank is one of the part of the processor. Interrupt controller is also a part of the processor. That we need to understand. And there is something like bus interconnect. So I code means what? The program, the code bus. There is a separate program bus. There is a separate data code bus. So instruction code, data code, instruction code, data code, and the system bus. System bus interface, the RAM and the peripherals. There are separate bus for RAM and peripherals. There are separate instruction bus. There are separate data bus for the program memory. And there is something like private peripheral bus, and there is something like debug access ports. So that's all. It's very simple architecture, and but very complex things are happening inside. Okay. So it is Cortex M3 or Cortex M4 processor architecture. What about this I code, decode system, private peripheral bus is tabulated here. I code is primarily for program memory, instruction fetch and vector fetch for the address 0 to 1F based on AMBA means Advanced Microcontroller Bus Architecture 3.0, Advanced High Performance Bus, Light Bus Protocol. These are all from ARM. We'll discuss about that in detail soon. So instruction code primary for program memory and data code primary for program memory. So code memory means program memory. So instructions are fetched from the code memory or program memory. Further, there is one bus. Data are also fetched from the program memory. Further, there is one separate bus. So this is parallel. While instruction is coming, data will also come because two buses are there. One bus for data, another bus for code. It's very interesting. Then there is a system bus for the RAM and peripheral. So for the data to bring from the RAM or the variables, we have a separate system bus which is coming through the PPB, private peripheral bus. Apart from private peripheral bus, there is something like AMBA high performance bus, light bus protocol. Then there is something like private peripheral bus, which is AMBA advanced APB, advanced high performance bus, here advanced peripheral bus protocol. And debug access port is for debugging kind of things. Okay, so that's all for today. I want to conclude with this now.